Good morning, students. Prusty sir again today to discuss a very critical problem in electromagnetic induction that is relevant to the time varying magnetic field. Okay, let's first see the situation. These are my credentials. First look at. In case of difficulty, you can contact me. Okay. So the question is, a time varying magnetic field B, capital B, exists symmetrically about the axis of a cylindrical region of radius capital R. This is a cylindrical region, cross section, radius capital R, and a time varying magnetic field B exists inside it. Is pointing along the axis of the cylinder. This is the axis of cylinder, passes through the center O, and it is pointing parallel to that axis into the plane. Okay, and the B is given by this. B is equal to B naught 1 minus small r by capital R, where B naught is the magnetic field at the axis of the cylindrical region. Of course, if small r is 0, then B is equal to B naught. So magnetic field at the axis is B naught. So that's what I written here. And this B naught also increasing with time. B naught is not, it is a time varying magnetic field on the axis, and it is increasing with time. The small r is the distance from the axis inside the cylindrical region. The small r is the distance from the axis of the cylindrical region. Okay, and that is inside the cylindrical region means small r must be less than capital R. So this implies small r must be less than capital R. Okay, fine. You can see the diagram. The small r at any small r value, B is given by this. Okay, maximum value of B is on the axis and is linearly decreasing, becoming 0 at capital R. Okay, the question is, at what distance from the axis of the cylindrical region should a particle of mass small m and charge small q be placed such that it will move in a circular path without any guide, without any other constraint? It can move in the circular path. Okay, fine. Then question 2 is, if the initial value of B naught and the speed of the particle are 0, initial values of the B naught and the speed of the particle 0, that time t is equal to 0, B naught is 0 as well as the speed also 0, means it is placed at this point. What will the kinetic energy particle at any non-zero value of B naught? B will increasing, so at some other value, non-zero value of B naught, what is the kinetic energy? That's what the question is about. Understood this? See the diagram. This is the cylindrical region of radius r. B is existing. B given by this. R is the distance from the axis, but is less than capital R. This is less than capital R, smaller than capital R. So B is not uniform over the area, as you can see. It's not a uniform magnetic field over the area, and also B naught is this B naught is, which is the magnetic field on the axis, is increasing with time and pointing into the plane. At t is equal to 0, B naught 0. That's essentially what is given in the question. But the question is asking, what is the, where should I place this particle having mass m and charge q so that it will move in the circular path as the B changes, maintaining this symmetry is the B changing. Then what is the location of this point particle, so that it will move on its own in a circular path with increasing speed of. Because since B is increasing, the induced non-conservative electric field, you must be knowing this, as the B changes, the non-conservative electric field appears. Because any field which is not produced by a static charge distribution is essentially non-conservative. So since it is not produced by any charge also, it's just produced by the time with the varying magnetic field or a changing magnetic field. So it is the field produced by changing magnetic field. So it is a non-conservative electric field and is a closed loop electric field. So ENC, due to symmetry in the charge distribution, this symmetry in the magnetic field distribution, it is a circular closed loop electric field. And which direction? Anti-clockwise map, as per the Lenz's law. Because if B is increasing, you put your right hand thumb in the direction of increasing field, then your four fingers will curl in clockwise direction, but there is a negative side, minus d flux by dt. So you reverse that clockwise direction, so you get anti-clockwise ENC. Okay, so ENC will be anti-clockwise. This is the ENC. This ENC is anti-clockwise. Nice. ENC, like this, anti-clockwise. Right. Right, so it is increasing. Okay. Very carefully listen to my discussion today. One such closed loop electric field line is shown in the above diagram in the red. This one I am hinting at this one. Okay. So what is the EMF in the closed loop? That is ENC into 2 pi r E dot dl integration over the closed loop, because you must be knowing this. In a closed loop. In this, let me write this one, so that I think you must be knowing this. So that's why I did not write. Now I am feel like writing this. Okay. From this I am writing this ENC to pi r is equal to ENC. You can take out. How can I take out ENC? Because ENC is a constant magnitude parallel to dl. As you can see here, it is parallel to dl. ENC and dl is parallel to this. So ENC dot dl is ENC dl. ENC is constant because of symmetry. I can't refer any point to any other point on this loop. So ENC must be same throughout all points. So ENC taken out and dl will 2 pi r is E loop. But that is also d flux by dt. What is d flux? Flux is how much? Flux enclosed by this circular area of radius small r. So how much flux it will be there, because B is not constant, is not uniform. So I have to take the B average into pi r square. For that I have to calculate B average. This is symbol of B average, less than greater than sign is the arithmetic average symbol, is the area average of over the circular radius r, B bar. So this B average into pi r square, the flux d by dt of that. So ENC into 2 pi r is pi r square, take outside, and d B average by dt. ENC is equal to r by 2 dB average by dt. Okay, cancelling pi r from both sides. So what is a tangential acceleration? Let me write also. You may feel that part I am writing is the tangential acceleration. Which leads to change of speed. So that is Q into ENC, that is force by m, mass. So Q by M R by 2 dB average by dt. Okay. So V is equal to a tau dt integration. This is dt cancel. So that is Q by M R by 2 B average plus C. But initial condition T is equal 0, V0, V0. So C must be 0. So V is equal to this. So this is the Q by M R by 2. That is B average. Right. But you also know from the motion of charged particle in the magnetic field, what is the radius of the circular path? R is mv by qb, where b is the magnetic field in which charge is moving. That is the magnetic field at the radius small r. So from this I get v is equal to qb r by m. B is the, not the average, b is the magnetic field on the circumference of that loop, because that is where charge is present. So but this expression of V are 2 now, but this is the V same. So this Q by M R by 2 B average and QB R by M both give the value of V. So equating both of them, I get B is equal to B average by 2. So that means the B on the circumference must be the area average of the B bounded by that circumference by 2. If this condition is satisfied, this charge will move without any guide, without any supporting extra support in a circular path. This is known as, this equation 4 is known as Bitatron condition. Okay. So you can refer to this Bitatron condition on my video lecture on 5th September 2025 on Bitatron condition. I have given that. Okay, let's find the B average first. So B average will how much? Take a small radius, some arbitrary radius r, thickness dr. So what is the flux in this small strip? B into B at that radius into area is 2 pi r dr. This area is 2 pi r dr. This area dA is 2 pi r dr. So the flux is B into 2 pi r dr. Is it okay? I'm clarifying the points as I go on. So this is B into 2 pi r dr, integration from 0 to r, the total flux divided by pi r square, the average, area average. Because you remember this. What is the B average? B bar is the area average of B over the circular region of radius small r. Okay. So what is the average then? Let us calculate. B into 2 pi r dr is the D flux total from 0 to small r, integration divided by pi r square. So this is a very small, very easy integration. B is B naught 1 minus r by r. Pi cancel, 2 outside. So r dr integration from 0 to r will cancel. After integration, cancel with r square. 2b by r square by 2. And this is r cube by 3r. 1 r square cancel. So 2b naught 1 by 2 minus r by 3r. This is the B average. So apply Bitatron condition now. B must be B average by 2 for the charge to move in the circular path without support. So B naught, that is the B on the circumference B naught 1 minus r by r, but the B average by 2 is this divided by 2. So 1 minus r by r, B naught cancel, 2 cancel, half 1 by 3 r minus r by r. So half is equal now, very simple thing, bring half to this side, r by r to this side, so 2 by 3 r by r is half. So r is equal to 3r by 4. Oh yeah. So if you place the charge at a location 3r by 4, then, and this is the distribution of B. As the B changes with time, it will continuously move on the circular path without any support. Okay, right? So that is answer to my question number 1. Then question number 2 from equation 1, that's what I wrote. ENC is R by 2 dB by dB average by dt. Already you have given you. So this is the ENC, but I have to find ENC at that location. R is equal to 3R by 4. So ENC is 3R by 4 by 2, 1 minus 2 by 3R into 3R by 4. So that becomes into dB naught by dt, because I told B naught is function of time. So 3R by 8 into 1 minus 1 by 2, 3R here cancel, 2 by 4 is 1 by 2, 1 by 2, dB naught by dt. The 3R by 16, dB naught by dt is ENC. What is a tau? Q by m ENC. So just Q by m you multiply here. That's it. Multiply dt to both sides. That's it. Then this is nothing but dt. So dt is this. Integrating both sides, b is equal to 3q by 16m b naught plus c. Initial time initially b naught 0, v 0. So c must be 0. So v is equal to this. So this is the velocity when b is equal to any non-zero value b naught. So kinetic energy is half mv square. Just I substitute this value. So 9 by 16, 9 by 16 square, that is 256. 1. So 9 by 512 q square r square b naught square by m. M1 m cancel by m1. The answer to question number 2. So it numerical data lesson. M is 1 gram, Q is 1 millicoulomb, R is 1 meter, B naught 1 Tesla. So if I K will be 9 by 512, 10 to the power minus 3 square, R 1 square, again 1 square, 10 to the power minus, when B naught on the magnetic field on the axis become 0 to 1 Tesla, what is the kinetic energy? So V naught 1 square, so divided by M is 10 to the power minus 3, 1 gram is 10 to the minus 3 kg. So this becomes 10 to the power minus 3, 9 by 512, 10 to the power minus 3, or 17.6 microjoule approximately. Okay, so this is what the answer to the question number 2. So 2 points to note here. The result does not depend on the manner in which B is changing with time. So it's linearly changing with time or changing with time in any complex manner matter, because finally my dt is getting cancelled here. Only change of dV is coming into picture. Change in B naught. That's right. But the spatial symmetry must not be compromised. It must be maintained. Okay. That's what. B can be changing with time in any manner, but the spatial symmetry, that is B naught 1 minus R by R is equal to B, must be maintained every day. Refer to my lecture on paradox in electromagnetism on 20th January 2026. Why I want you to refer this? Because initially it was having zero angular momentum, the charged particle. Now it is getting angular momentum just by switching up the field, or increasing the B. So I am not giving an external torque over there. In this system, there is no external torque, but even the angular momentum is gained by the revolving particle. So this angular momentum is as I told you, the angular momentum is stored in the both places, the electromagnetic field as well as with the momentum. So even if zero angular momentum and I am not physically rotating this, external torque, the mechanical torque I am applying, but still it is getting angular momentum. So this angular momentum stored in the electromagnetic field, you will get an insight from my discussion on the paradox in electromagnetism on 20th January 2026. And Betatron condition I have discussed in on which date? 5th September 2025. Okay. So this is a very important point. Now even if I switch off the magnetic field suddenly, the change of magnetic field will become 0. The change of magnetic field will become 0. So this, instead of V naught, it becomes 0 to 0. So V will be 0. It suddenly come to rest. Understood this? Initially, there is no magnetic field. There is no angular moment. There is this charge at rest. I switch on the magnetic field, then I suddenly switch it off. So finally, this change in this will be delta B naught, delta V. Delta B naught becomes 0. So V will become 0. It will gain speed and again suddenly become 0. Okay. If I switch off this. So that also confirms your conservation of angular moment. Okay. Provided you consider angular momentum stored in the electromagnetic field as well as in the mechanical system. Okay. Thank you all. I think you have understood this. Okay. Angular momentum part will give a bit short script here, because this is angular momentum stored in the magnetic field, electromagnetic field is not in your syllabus. But up to that, up to note point 1, you have to understand very clearly. And if anybody asks this, you can answer the question: the kinetic energy gained by the particle. Okay. This, once you get the speed, you get angular kinetic energy. Okay. Did you understand my whole discussion here? There is a series of discussion here on the critical problem section. So critical problem, this is part 1. Part 2, part 3 will follow. Okay. So hold your breath. I'll discuss one after other the conceptual issues involved in this type of electromagnetic induction situations. I hope you have understood all of it, and I advise you to go through it again to get a full grasp of the discussion. But this is very important for you. This is not out of syllabus. This is perfectly within our syllabus. Okay. Thank you all. We'll meet very soon with the part 2. Okay.